All right, so we can finally talk about chemistry instead of just converting units. So first we're going to talk about atoms, atomic structure, periodic table, talk about some trends on the periodic table. Also talk about chemical and physical changes. Okay, so you guys hopefully are all familiar. Everything is made out of atoms and molecules. Certain atoms of certain types, certain molecules of certain types have properties. When we're talking about physical changes, talking about changing a substance in some way, that does not change the fundamental arrangement of its atoms or molecules. The substance is still H2O in this case. So it's H2O, which means 2 hydrogens, 1 oxygen. When you boil water, it's still H2O. It's just now a gas. Same molecule. Chemically, it's unchanged, even though physically it's changed. A chemical change then means that we're altering the fundamental structure of the molecules or the atoms. So something here, if we were to draw this as a model, the iron atoms in something like a nail before it's rusted are all very nicely arranged. And that nice arrangement gives them structure, gives them strength. When iron oxidizes, we're actually inserting oxygen atoms inside that structure, and it destroys the structure of the iron, making it weak, making it flake, also changing the color. So fundamentally, a chemical change is a rearrangement of atoms at the most fundamental level. Right? It becomes a new substance. Sometimes this can be hard to decipher just by looking at things. Usually something like a chemical change is going to have some color change to it, although there are color changes that are physical. We'll see examples of that. So this is an example of a physical change. This is dry ice. Dry ice is fun, as long as you're playing with it safely. Don't touch it because it's cold enough to give you frostbite. Yeah, freeze your skin. But it's carbon dioxide. And so when it's a solid, it's all these carbon dioxide atoms, or molecules, excuse me, stuck together by intermolecular forces. As it warms up, it goes straight from a solid to a gas. And we haven't changed it, it's still CO2. See over here, yeah. So it's CO2 as a solid and it's CO2 as a gas. It's just, as a solid, they're packed closer together. But that's not changing it fundamentally. Sugar dissolving is another physical change. So in the crystal structure, solid sugar, this can be harder to see. And it doesn't get much better when I zoom in because it's so pixely. So if you squint, it actually looks better. These sugar molecules in here, they're lined up and they form a crystal structure. But the bonds that hold them together are not true chemical bonds. They like to stick to each other, but they're still individual sugar units with this formula. When you add them into water, that water is able to separate out individual sugar molecules. And they're still sugar, right? And probably from tasting sugar in a drink versus solid sugar tastes the same, or at least similar. It's the same molecule, fundamentally not changing. Chemical change, on the other hand, breaks those molecules apart or builds up new molecules or recombines in a number of different ways, possible ways. So propane is this molecule, it's C3H8, so 3 carbons, 8 hydrogens. And whenever you burn anything, burning is a chemical change. So when you burn this propane, releases heat, but it also takes all of these carbons and rips them apart. They react with oxygens and they form carbon dioxide. And it also forms water because the hydrogens react with oxygen also. Looking at these two pictures, right? Both pictures, very different. But all of the carbons and all of the hydrogens from these propane molecules become the carbons and the hydrogens in these CO2s and these water. We're taking one compound, splitting apart the atoms, making new molecules out of it. Okay, so that's physical and chemical changes. Right? Anything that changes the fundamental structure of that molecule or the atoms, rearranges them. We talk about physical and chemical properties. It's a similar thing, but it's more about how does it react with, or how does it appear in different situations. So physical properties, I guess you can think of physical properties as being passive, right? A thing's physical properties are evident by just looking at it. Even by smelling something, you're not changing the structure of the thing that you smell. It's that molecule fitting into a receptor in your nose and telling your brain, hey, this is that receptor. So like the smell of gasoline is just because gasoline is the way it is. It's the shape of the gasoline molecule. So odor as well. Odor, taste, color, appearance, and then things like melting point, boiling point, and density are all physical properties. And those are all things that we can measure or know about something passively without changing its chemical structure. So physical properties can be exhibited as physical changes. That's like melting point, boiling point. Chemical properties, you can only figure out the chemical properties of something by reacting it with something else. It's a property that a substance displays only by changing its composition, meaning it has to undergo some sort of chemical reaction for it to be a chemical property. So a chemical property of gasoline is that it's flammable. That if I add enough heat and I add oxygen, it will react and become carbon dioxide and water. Corrosiveness is another one that's a chemical property because corroding something is usually reacting with it. Acidity is a chemical property. We'll talk more about that. In Chem 20, you probably got just like a real basic idea of acidity, but it's how it usually reacts in water. And even toxicity, right? There's some things that are toxic, not because the molecule itself is toxic, but because of the way that your liver digests it and oxidizes it, that turns it into a toxic substance. Methanol is one of those. Methanol by itself, not toxic. Methanol after your liver gets a hand of it, toxic. So one of the ways actually that you can treat methanol poisoning is to give somebody a shot of vodka, because the ethanol can outcompete the methanol, and then your body will eliminate the methanol without really digesting it, without your liver oxidizing it. Don't test that at home. There might actually be better ways to do that, but that's one way. Okay, so real quick, so we're right about at the end of our time. Take a second. Look at these. Write them down. Trying to decide if they're physical or chemical properties. All right, so for A, who thinks that this is a, actually no, I won't make you raise your hands, but chemical or physical property? Why? It's changing the shape of it. Yeah. Hammering it does nothing to make it a new substance or to react it with anything. Copper wire hammered flat is going to be physical. Does anybody know what that property, that physical property of metals is called? Malleability. Things that are malleable can be, I don't know, basically squished without completely deforming. Or I guess they could be plastically deformed. Okay, a nickel dissolves in acid to form a blue-green solution. Chemical. Part of the key to this is that it's dissolving in acid and it's forming a solution that's got a different color, supposedly, that it wasn't blue-green before. So it's a chemical property. So those nickel atoms are being ripped apart and forming ions, complexes, make the solution blue-green. Dry ice subliming. Physical change. Yeah, subliming, I think, or sublimation throws people off because maybe it's not a word that you've heard before. It just means that it's going straight from a solid to a gas. So just like boiling is going from a liquid to a gas, still a physical property or a physical change. A match ignites when struck on a flint. Chemical. Fire. Alrighty. So energy is the reason that things happen, mostly because energy is spreading out. We don't really talk about that in this class, but it's one of the laws of thermodynamics, basically, that entropy increases, essentially energy spreads out over time. So we got a bunch of different types of energy. Kinetic energy, it's the energy associated with the motion of an object. So I always like to throw something. Kinetic energy. Right? Potential energy is the energy associated with the position of an object. These are probably dry markers, right? So if I hold this up high, it's got potential energy. Hold it lower, it's got less potential energy. All right, so potential energy. Thermal energy is the energy associated with the temperature of an object. That probably makes sense. Something you maybe didn't know is that when you drop something, so like this weight coming off the top of the building and hitting the ground, it's probably not going to bounce. And if the concrete doesn't break, the energy is not destroyed, it doesn't disappear. That energy becomes thermal energy, so it gets turned into heat. So my Chem 20 class is actually with this, basically this exact same slide. I forgot to add it in here, but talk about how much energy it takes, because it's the same thing. Like if I slap this desk, that energy gets turned into thermal energy just a little bit. So somebody asked the question and did all the math to see how many times you would have to slap a chicken to completely cook it. And it's a lot. And then they were like, okay, that's like a bunch of like regular slaps. And again, you got to make a lot of assumptions, like it doesn't cool off in between slaps, or that just the wind from your slap doesn't cool it off. You Googled it? How many slaps was it? 23,034. Yeah, it's 23,000 slaps. It's probably the same. Usually just, it's the first website that comes up. Do they have on there how fast you'd have to slap it once?
It would take at least 23,034 slaps with a velocity of 3,725.95 miles per hour to cook a chicken at 400 degrees Fahrenheit or 205 degrees Celsius. And then it puts in, however, this is not at all realistic.
No. Because after you slap the chicken 1,000 times, it's probably just pieces. Also so gross.
Minimum 135 slaps, 1,000 slaps across as many as 8 hours to slap the chicken.
Yeah.
If you're committed to it, slap the chicken for 8 hours.
It's not going to work. Never going to work. Yeah, the other website that I found, it said like the speed, if you wanted to slap it once and convert enough kinetic energy into thermal energy to cook it, it's 3 times the fastest man-made jet. So you'd probably just obliterate the chicken and everything else around it, including your arm and hand. Anyway, so thermal energy is energy associated with the temperature of an object. It's these, and really it's a kind of kinetic energy, but we don't really talk about it most of the time in that way. That'll come up more when we get into gases. Anyways, that's different types of energy. So this law of conservation of energy is neither created nor destroyed. And in chemical reactions, we often track the amount of energy. And if you take Chem 2, you'll do a lot more of that. A lot of that class is spent on basically just calculating energy changes for different chemical reactions. So you can change energy from one type to another, one form to another. Whoops, removed. Yeah, it does. That's why the window's open. I can bring a candle. That might just add on top. It is humid. It's gross. But at least there's enough seats for everyone. So energy can flow from one object to another, so we can move energy around, and the total quantity, though, is constant and always spreading out. And objects with high potential energy tend to be unstable. In terms of chemistry, you have chemicals with high chemical potential energy, and those are usually explosives because they're unstable because of how much energy. we'll talk more about energy later, but for now, energy is always conserved, right? So we're never losing energy. It's just moving from one place to another. We're being converted from one type to another. And then systems with high potential energy tend to change in a direction that lowers their potential energy, releasing that energy into the surroundings. All right, so you take gasoline, you burn the gasoline, it releases energy. We turn that energy into kinetic energy, but it's really hard to go the other way and take those exhaust molecules and recompress them back into the gasoline. Not that it can't be done, but you have to actually put more energy into the reaction to make that happen. It's just not worth it, at least so far. All right, cool. So that's energy. Check. So the atomic theory basically is the idea that everything's made out of atoms. You might have already known that. And I'm going to try and give you a sense, because we're going to look at the law of conservation of mass, the law of definite proportions, the law of multiple proportions. And I gave you like a little video on this because last week we didn't get to it, but it was part of the modules for Alex. And these are the ones, definite proportions, and specifically multiple proportions. That's the trickier one to calculate, or trickier one to wrap your head around. But you got to go back and think back to when they didn't know these things. Because we have the benefit of modern science and just knowing that the world is made out of atoms and molecules. And if you've taken Chem 20, like you've talked pretty extensively about molecules. But you got to think back to, when they didn't have that. So I came up with a pretty unhinged analogy. Not for this will make sense. Right? So when you burn wood, does the mass change? If you weigh the wood before and after, the mass changes. Yeah. No duh. But what if you contain the wood and burn it in an airtight container? Then you've made a bomb. But if you set things up correctly and you're like got a really strong container, right? You burn the wood in this container so nothing is able to get out and it doesn't explode. Is the mass going to change? Some people saying yes, some people saying no. So the mass still not going to change. Or I said, sorry, it's not still not going to change. The mass isn't going to change. So when you burn wood, you're changing the wood from one thing into another thing, and usually that thing just floats away, right? It's CO2, it's water vapor, it floats away. But if you contain it, and so this was the experiment that, or basically the experiment that led to Lavoisier coming up with this law of conservation of mass. He's probably not the first person, but just looking back in recorded history, 1789, that's a pretty long time ago. One of the first sort of modern-ish scientists to come up with this, right? In a chemical reaction, matter is neither created or destroyed. Our total mass, the substance, doesn't change. The atoms, though, they rearrange during a chemical reaction. And so like for something like gasoline, which would be why did I decide that I'm going to draw this whole thing out? Gasoline, if you didn't know, is a lot of different stuff. But this is one component, octane. Lots of carbons, lots of hydrogens, and nothing else. But when you burn this with oxygen, it rearranges, and you get a whole bunch of CO2 plus water molecules, as long as it burns completely. All right, so we just take this and we chop it up, and it becomes these smaller molecules. And as far as this class is concerned, if you want to talk about radiochemistry or radioactive stuff changes, but for the purpose of this class, they're indestructible. Right? Any of the reactions that we're going to do is not going to change the identity of these atoms. And when we do reactions, we're just rearranging them. So yeah, it was Lavoisier. He burned stuff in sealed glass things. I'm sure some of those exploded on him. But if you took sodium, for example, and chlorine, this will get to something that we'll talk more about later too. Right? Chlorine's a gas, sodium's a highly reactive metal, basically just explodes when it comes in contact with water. If you mix 7.7 grams of sodium and 11.9 grams of chlorine with a total mass of 19.6, assuming that it all reacts, you get exactly 19.6 grams of sodium chloride. No more, no less. Now, most of the time when you guys are doing reactions or in like real life labs, you do the reaction and then you have to filter it and transfer it, and it doesn't go to 100%. Some gets left behind on the glassware, maybe you spill a little. So these things don't come out exactly the same, but it should always come out to be a little bit less, if anything. And that's just because you lose some to different places. So when a log completely burns at a campfire, the mass of the ash is much less than the mass of the log. So what happened to the matter composed the log? Anybody think it's A? Yeah? B? This is a little bit weird because, yeah, it like releases a lot of heat. Although the wording of this, I think, is a little bit tricky. You want to say it might be B because it says the matter converted into energy and we get heat out of it. We're not actually converting any matter into energy. Those are nuclear reactions, nuclear chemistry. That's the word I was looking for earlier. Nuclear reactions convert matter into energy. But this reaction, that's not going to happen. And then the matter that composed the log is still present in the ash, but has much lower mass. The mass isn't going to change, so it is A. It reacts to form gases that are released into the air and also releases a bunch of energy as heat. This one spot is so squeaky. Okay. The law of conservation of mass. Basically, everything that goes into a reaction has to come out in some form on the other side of the reaction. Shouldn't be losing anything. All right, so the law of definite proportions. The big fancy way to put this is all samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. In short, every molecule of a pure compound is the same. Meaning that if I've got a molecule that has like water, 1 oxygen and 2 hydrogens, doesn't matter where the water comes from, it will have 1 oxygen and 2 hydrogens. And this is one of those ones that I think is hard to appreciate the importance because you already know what molecules are. You already know that a pure compound is going to be identical to any of the same kind of compound. So this is where my unhinged analogy comes in. I hope this helps get across the importance of this. So I call it the law of definite pizzas. So imagine one night you order a pepperoni and sausage pizza from, anybody give me, huh? Me and Ed's, okay. So the next day you order, so you get that pizza, you eat it, you're like, all right, yeah, that was pizza. And then for some reason, you're just really on a pepperoni and sausage pizza kick. So the next day you order a pepperoni and sausage pizza from somewhere else. Domino's. Would it be ES? Anyways, does that feel wrong? It's just an S.
It's just OS.
Is it apostrophe? Anyway, sorry. Okay, and imagine you're a big old nerd like me, and you're bored, and you count the toppings on there, and you find that there's exactly 27 pepperonis, and there are 52 sausage bits. You're thinking back to that other pizza that you had. You're like, how many were on there? And so being the foodie that you are, you look at the picture of the first pizza. It's me and Ed's pizza. Maybe if it was something fancier, you might actually take a picture. And then you count those, and that one's got exactly 27 pepperonis and 52 sausage bits. It's weird. Might be a coincidence. So you dig a little deeper. You descend into madness. Maybe it's just a weird coincidence, but you order a third pizza the next night. Different place, pepperoni and sausage. That one's got 27 pepperonis and 53 sausage bits. Exactly the same as the 2 other pizzas, even though it's the third place that you've gotten a pizza from. Is it just a weird coincidence? So you drive up to Fresno. You get a pizza there, 27 pepperonis, 52 sausage bits. The same 1-to-2 ratio. Then you look at pictures on Google, Instagram, anywhere. Every single pizza that you look at has the exact same ratio. That would be weird. That would be notable if every single pizza that had pepperoni and sausage was the same. Sorry, I got one more slide on this. I maybe could have stopped there. Could it be a prank? Has nobody else noticed? Right? This is, what was his name? I forgot what his name was. Proust, Joseph Proust, coming up with this law of definite proportions. He's like he's analyzing these samples, he's breaking them down, and he's looking at these ratios, and he's like, it comes out to the exact same thing every time. So you fly to another state. Now you're starting to dump money into this. And you even notice that there's patterns in other pizza toppings. So it's not just pepperoni and sausage. This is probably similar to Proust, right? He's doing this thing and this is weird. It's weird that it's a specific ratio, right? Because if you actually get a pizza, it's gonna be some random number of pepperonis, and a random number of sausage, a random number of every other topping. But in molecules, it's all going to be the same. So anyways. So the law of definite proportions, again, says that if we look at any compound, no matter where it came from, no matter how it was created, it will have the same ratio of masses. And if we were able to count the individual atoms in the molecules, the same number of each type of atom, it will have the same ratio of their constituent elements. So something like, what was this one? Water. Right? So you can decompose water, you can collect all of the oxygen, and you can collect all of the hydrogen. And for every single sample, that will be a ratio of 8 or 8:1. Here, the 8 being the oxygen and the 1 being the hydrogen. So there's this weird consistency. It makes sense if you already know atomic theory and we already know that things are made out of atoms. But predating that, be wild. So really the end usefulness of this is that it's one way to determine if you've got, or I guess it's one way to determine if you've got the same compound. Like the lab that you'll do tonight, if you have lab tonight or Wednesday, there's other ways that you can identify compounds and distinguish them from different compounds. But this is one way. So if the mass ratio of nitrogen to hydrogen in ammonia is 4.7:1, and a sample of ammonia contains 10 grams of hydrogen, how many grams of nitrogen does it contain? So what does this 4.7:1 mean? 4.7 of what to 1 of what? Nitrogen to hydrogen. So this is 4.7, not just nitrogens, but grams of nitrogen more specifically, to 1 gram of hydrogen. So ratios can always be rewritten as a fraction like this. And a fraction that looks an awful lot like a what? Conversion factor. Okay, so if we start with 10 grams of hydrogen, we can multiply by this conversion factor and figure out how many grams of nitrogen we should have. 10 times 4.7. Whoops, not 4.7. 47 grams of nitrogen. So you can use mass ratios of a compound to figure out how much of different elements are in there. 47. Cool. Yeah. Thank you. No. Good. Yeah. All right. I don't want that to be a distraction. Any questions about this? Okay. All right, so if we've got 2 samples now, carbon monoxide, are decomposed in their constituent elements, meaning we take the carbon monoxide, we break it down into carbon and oxygen. One sample produces 17.2 grams of oxygen, the other, and 12.9 grams of carbon. The other sample produces 10.5 grams of oxygen and 7.88 grams of carbon. So show that these results are consistent with the law of definite proportions. So how do we do that? Ratios, yeah. So really, for each of these, we just want to know the ratio of grams of one element to grams of the other element. And we want to be consistent in the way that we do that. So it's either going to be oxygen divided by carbon or carbon divided by oxygen for both of them. Otherwise, we'll get ratios that don't match. And a lot of the time you want to do, if one is larger than the other, so if I'm looking at 17.2, 12.9, I will want to do 17.2 divided by 12.9 just to get a number larger than 1. So for my first sample, 17.2 grams of oxygen divided by 9 grams of carbon. And then for my other sample, 10.5 grams of oxygen divided by grams of carbon. So this is 1.33. Is it consistent with the law of definite proportions? Yeah. We say both of these are probably carbon monoxide. All right, so the law of multiple proportions, I don't have some sort of unhinged analogy for you for this one. But it's a similar kind of thing that, like, and I think from this wording it can be confusing, but it's a pretty simple concept at its core. So when two elements, call them A and B, form two different compounds, the masses of element B that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. The law of multiple proportions is comparing different compounds, just write this in, different compounds of the same elements. Had a moment of deja vu because I wrote exactly that, or something very close to that, in the video I made. So law of definite proportions is we're comparing the same compound from different sources. We're looking at one thing. The law of multiple proportion is looking at different compounds. Yeah. So the law of definite proportions is when I'm saying I got this carbon monoxide sample from somewhere, and I got this carbon monoxide sample from somewhere else, or created it a different way. Those two things are both carbon monoxide and will have the same proportions of carbon to oxygen. For multiple proportions, as we'll see in the example, we're comparing two different compounds made out of the same elements, different numbers of the same elements. So like down here, if we think of, again, generic element A and element B, then I could have a compound of A and B that's 1A and 1B. Or I could have 1A and 2 Bs. I could have 1A and 3 Bs. So we're just changing the number of one of them. And this is what kind of led to knowing that, like, our atoms could combine in different ways, and we would get different compounds with different properties. And it also hints at the fact that it's discrete numbers of each type of atom. We'll see that a little better in the example. Okay, so carbon monoxide has 1 carbon and 1 oxygen. Cool. Carbon dioxide has 1 carbon and 2 oxygens. So if we just weigh the oxygen from each, how much more will the oxygen from carbon dioxide weigh? It's twice the amount. because carbon dioxide has twice as many oxygens as carbon monoxide. Now, when we're trying to compare masses of these, we're not going to be counting individual things, but between these two, we should always expect that ratio of carbon to oxygen for one to be twice as much as the carbon to oxygen for the other. So if we weigh just the oxygen, it'll be 2x, 2 times as much. So if we had carbon trioxide, how much more would that oxygen weigh than carbon monoxide? 3x. So that really is like the basic idea of multiple proportions. Now, the math, I think, can feel confusing because we're looking at masses for this. And so we have to normalize everything, meaning that we have to calculate the definite proportion for each, and then we divide the definite proportions to get the proportion between them. So again, carbon monoxide, carbon dioxide. If we had a sample of carbon dioxide or carbon monoxide, we could take the mass of oxygen, we could take the mass of carbon, and we could calculate, basically divide the mass of oxygen, this is grams of oxygen, by the mass of carbon, and we get this 2.67 grams to 1 gram. And for carbon monoxide, we get 1.33 grams per 1 gram. And so all we're doing down here is we're taking the ratio of carbon dioxide's 2 to 1 and carbon monoxide's 1.3. So 2.6 divided by 1.33 equals 2. So calculate the definite, this is the definite proportion. This would be the definite proportion. And then you divide those. Should have already done that in Alex. Questions? Maybe we have an example. Helps to work through these. So hydrogen and oxygen can form both water and hydrogen peroxide. So 2 different compounds, both made out of hydrogen and oxygen. The decomposition of a sample of water, so we take water and we break it down, we'll get 0.125 grams of hydrogen to every 1 gram of oxygen. If we take hydrogen peroxide, do the same thing, we'll get 0.0625 grams of hydrogen to every 1 gram of oxygen. So really, they've already calculated the definite proportion here for us. Right, I can write this as 0.125 grams of hydrogen for every 1.00 grams of oxygen, and that's for water. And then 0.0625 grams of hydrogen for 1.00 grams of oxygen. And that's hydrogen peroxide. So now how do I show that this is consistent with the law of multiple proportions? Yeah. Now which ones should I, what order should I divide? Mm-hmm. But which one do I put on top? Which one do I put on the bottom? Larger one on top. It's pretty much always the larger one on top. So the larger one, 0.125. So I put 0.125. And we can simplify this because it's per 1. So I can just do 0.125 divided by 0.0625. And that's going to be 2. Okay. So it is consistent. And if I draw out water, actually I'll draw it out this way, and hydrogen peroxide, so the ratio here, we've got oops, 2 hydrogens per every 1 oxygen compared to hydrogen peroxide, where it's only 1 hydrogen per every oxygen. And so that's why when we look at the ratio of ratios, means that there's twice as many hydrogens per oxygen in water. Okay. I'm not sure that actually comes up that much more. Maybe a little bit. All right, so cover laws. All right, so now a little bit of history of the atom and like how we got to the modern theory of the atom. And mostly just talking about the parts here. So we're going to go over like atomic theory and structure of the atom. And I'll give you a slide basically of what you actually need to retain from this. And it's a lot less than we're going to cover, but there's a few concepts here. Because Rutherford's nuclear theory was a little bit incomplete, but he got a lot of things right. So the first thing that he got right was that an atom's mass and all of its positive charge is contained in a small core called the nucleus. So the center of the nucleus has all the positive charge. He also got this right, that the mass of the volume of the atom is mostly empty space. And then it's got these tiny negatively charged electrons dispersed in that space. We'll talk more about how they're spread out. And 3, even for a neutral element, he was correct, that there are as many negatively charged electrons outside the nucleus as there are positively charged particles, called protons, within the nucleus, so that an atom is electrically neutral. He was mostly right. He was missing one thing, though. And scientists pretty quickly realized this because hydrogen, this worked for. Hydrogen has 1 proton. Helium has 2 protons, but the mass of helium is actually 4 times that of hydrogen. The reason is that Rutherford's theory left out neutrons. And so there's this other particle that has a similar mass to a proton that's also in the nucleus. And actually, it's not in these slides, but the neutrons actually exert, or they add something called the strong force. So the force that holds the nucleus together is called the strong force. Because 1, you've got these positively charged things that are directly next to each other, and like charges want to repel each other. So in order to get more than 1 proton next to each other in a nucleus, you have to have something else that also has the strong force but no charge. That's what neutrons are. So this is something you need to know, and again, it'll be on a highlight slide at the end, but neutrons have no electrical charge, and the mass of a neutron is similar to that of a proton. So hydrogen atom, 1 proton, no neutrons. Helium atom has 2 protons and 2 neutrons. And for the most part, the number of neutrons and the number of protons is approximately equal as you move up the periodic table, up to a certain point, and then you start needing way more neutrons than you do protons. Okay, so those are neutrons. This is one of those things that's, again, hard to grasp, but I found something that'll hopefully make this a little bit more relatable. When we're talking about the structure of the atom, the nucleus is extremely dense, contains over 99.9% of the mass, but really occupies almost no space. It's right at the center, very tiny. And we use this analogy of a cloud. So these electrons are like a cloud that's surrounding it, right? If you've flown in an airplane before, airplanes can fly up and straight through clouds, right? They basically have no mass and nothing to them. But if there was another airplane in the middle of the cloud, that's what you would hit. So the nucleus is that other airplane in the center of the cloud. And yeah, the electrons have negligible mass, basically meaning we don't count the mass. It's so small, barely matters. And so they're mostly empty space. And because of that, matter is actually less uniform than it appears. So if you could zoom in far enough on something with a microscope, you'd see this space in between the nuclei. So as an analogy, a grain of sand composed of solid atomic nuclei would weigh 11 million pounds. So if you had a grain of sand that was only made of nuclei and we took out all of the space, it would weigh 11 million pounds. And that might be getting close to heavy enough to be a black hole. There's also, does anybody know, aside from black holes, what the densest object in the universe is? Neutron stars. Why are they neutron stars? They're made of neutrons, all closely packed together. All the electrons have collapsed into protons, and it's just a ball of neutrons. So way more than a grain of sand, but the same idea. Found a different picture to put in here. So scaffold, book uses this analogy of scaffolding. So this is scaffolding. Probably seen it around buildings that are being worked on. And this isn't exactly from super far away, but if you get farther and farther away, it looks more and more solid. And if you can zoom in, then you start to see that there's lots and lots of gaps in between. And it's actually mostly just empty space. So like when you're tap your knuckle on the table or just touching anything, you're not really touching it. Your electrons are repelling each other, and it's one scaffold up against another, which is really weird. So I was just thinking of superpowers and like the ability to like pass through a wall or something. If you could turn off the repulsions between your atoms and the ones in the wall, then you would be able to just pass straight through it.
You
Yeah.
seem to be flush, or would you anything flush related?
Some. Oh, he does that?
Yeah, he vibrates at the natural frequency of air, so his molecules are in such an excited state that they pass them. I'm sorry, I'm a big nerd.
And no, I was just thinking about, could that actually work? Could you actually vibrate at a specific frequency and then pass through an object? I don't know.
Yes, it's science fiction. So
It is. I'm sure there's somebody who's actually done the math on that. No, you're good. Anyway, so matter appears solid basically because we can't see through it. Where did I want to actually slide this? Okay, this is a good place for this. All right, so I found this. Turn that on. Okay, so basically, this website is saying, this is going to work, right? There's the mouse. Yeah, okay. So this is proton. If we said a proton is this big, then assuming the resolution of the screen, so I don't know if it's exactly accurate for this, but the screen would need to be 11 miles wide to show the electron for this proton. And you can see the scroll bar at the bottom. So just to give you an idea, because I've got this fancy mouse and it can scroll really fast. Someone showed me this is really funny. Right, just to show you, if I'm just scrolling on the trackpad, I can go, yeah, pretty good speed. This goes on forever. But on this, is it scrolling in the right direction? Yeah, so I just flick that on the mouse and it free spins and it'll just, should just keep going. Oh no, it is going. You just can't see it refreshing. You can see this moving down here. So if I go back up, well, 11 miles. Gosh, why is this not? Yeah. Anyways, right, so we go pretty quick. This horse is long, but, and I have to hold the shift here. So I'm just gonna hit shift and then scroll. You see how much that little scroll bar at the bottom's not moving? The very bottom left. The mouse wheel's still spinning. So I'll stop there and then I'll just grab this. So we have to go all the way out here and then for some reason it doesn't show up. But this is where the electron would be if the proton was that big. Just so much empty space. Okay. All right, so it's mostly empty space. To talk about this, again, the mass of these objects, we're talking subatomic particles. So these are the things that make up the atom. Proton is 10 to the negative 27 kilograms. Neutron, very similar mass, 10 to the negative 27. Mass of electron, 10 to the negative 31. So even smaller. What is that, about 10,000 times less massive than a neutron or a proton? So if you had like a baseball, then your electron would have the mass of a grain of rice by comparison. Not much else to say about that. So the atomic mass unit, like when we look at a periodic table, these are actually in AMUs. If I pull this up. All right, so on here, each of these masses is actually in AMUs, atomic mass units. And we'll get to, hopefully today, why they're not exact. Those are all atomic mass units. So what is an atomic mass unit? Basically, because protons and neutrons are so tiny and not massive at all, had to invent a new unit to be able to talk about them. Conveniently, at least, right? Because we could do it in kilograms and always talk about this 10 to the negative 27, but it's a lot easier if let's just define a new unit for this entire field of things that are so small. Carbon being one of the more abundant elements, especially on the surface of the Earth. They took carbon and they said, okay, if we take a carbon atom that has 6 protons and 6 neutrons, whatever that mass is, divided by 12, right, number of protons plus neutrons, we're going to call that 1 AMU. So really, 1 AMU is the mass of a proton or neutron. It's not exact, but very closely the mass of a proton or neutron. So then for any element, if we know the number of protons and neutrons, we can figure out what its mass is in atomic mass units. AMU. So even though the proton and the electron, massively different masses, they have the same but opposite charges. So a proton is a +1 charge, an electron is a -1 charge. Neutrons are neutral. At least with proton, P, positive. Neutron sounds like neutral, no charge. The electron, then you just have to remember, is negative. So if we pair any proton with any electron, they cancel each other's charges out for a net charge of 0. I think that was one of the ALEKS modules you had to do that kind of thing. And if you ever have an imbalance in the number of protons or electrons, that's when you get charged atoms or charged particles. So this table is going to be useful. It'll come back up in a second. Most of the time, matter is charge neutral because charges are unstable. It represents really a high energy state. And so those charges will balance themselves any way that they can. Even when we're talking about chemical reactions, there's almost always what's called a counterion. So you do a reaction, or if you've ever trying to think of a specific one, a lot of over-the-counter drugs will be something HCl. The HCl is a counterion in there. Or providing counterions. So one example of these charges balancing themselves in dramatic ways are static electric shocks or lightning. Lightning's really cool because there's almost always, if you can super slow-mo the lightning, you can see the tendrils reaching out from the cloud, and then one of them connects, and then that's where all of the charge is balanced through. All right, so here's the summary of basically everything that you need to know about really atomic theory and structure of the atom. This table, you don't need to memorize these masses. You just need to know that one proton is really light. You need to know that a proton and a neutron are about 1 AMU, and an electron has basically negligible mass. You need to know that a proton's a positive charge, a neutron is neutral, and a electron is negative charge. Atoms are mostly empty space. Protons and neutrons in the nucleus. Electrons surrounding that, and positive and negative charges cancel. And that pretty much sums it up. Moving on now, we got all those things down or refreshed from previous chemistry classes. How do we define elements? So it turns out elements are defined by their protons. If you change the number of protons, you change the element's identity. So helium always has 2 protons, carbon always has 6 protons. That never changes. And the symbol somewhat frustratingly for us speaking English, atomic number is Z, which comes from the German Zahl, which means number. So really it's just the element's number. So you just got to remember that's Z. And of course we have A also as another variable, but the number of protons in the nucleus defines the element. So you got a real basic periodic table. In every single one of these, the number at the top is the atomic number, which is the number of protons. And so they all have a unique number all the way up to 118. Chemical symbols and names, yeah. So each element is again defined by a unique atomic number and a unique chemical symbol, 1 or 2 letters. There's a lot of them that are based on English names, but some, like sodium, a lot of natrium. Does anybody know another one? Willing to volunteer? No, some of you guys know these. Huh? Oh, just like elements that are named after or have their symbol from a different language other than English. Potassium. All right, potassium is K. Do you know where it comes from? It's wow. Now I have to spell it. Is it just calcium? Selenium? Wow. It's selenium, right? Anyways, selenium. I think I spelled that wrong. Gold, yeah. Gold actually is like aurium, AU, I think. And sodium, natrium. Mercury is another one that's Hg. Yeah. So a lot of them make sense. Some of them don't. Potassium and phosphorus will probably trip people up the most. Okay, so isotopes. So while the number of protons is always the same, you can have different numbers of neutrons. And pretty much every element has an isotope, or I should say 2 isotopes that have different numbers of neutrons. One is more common than the other usually, although sometimes they occur in relatively similar abundance. So same number of protons, but a different number of neutrons called an isotope. So all neon atoms contain 10 protons, but they might have 10, 11, or 12 neutrons. So the relative amount of each different isotope in a naturally occurring sample of a given element is roughly constant. And so that's why we call this the natural abundance of the isotopes. So this is why on the periodic table, I should do a periodic table. Oh, well, we'll get to it in a sec. You change the number of neutrons, not the number of protons. Ah, there it is, the mass number. So the mass number is represented by the symbol A. Don't get it confused with the atomic number, which is Z. The atomic number, or sorry, the mass number is always the number of protons plus the number of neutrons. So for any isotope, you'll have the chemical symbol, and then as a subscript in front of it, you'll have the atomic number, and then the mass number will be a superscript in front of it. So for example, 3 isotopes of neon, all of them have 10 protons, and then they have different mass numbers. You have to calculate how many neutrons there are. It's not too hard though, because it's set up the way you need to calculate it. Because the mass number minus the number of protons will give you the number of neutrons. So for neon 20, it'll be 10 neutrons. For neon 21, how many neutrons? 11. Sorry, And for neon 22, 12. I'm just using N for neutrons. So another common notation, because, and this is where one of those things where it's chemists are lazy when it comes to nomenclature. They want everything to be written as shortly as possible. Another way to write out these symbols will be isotope symbols, will be the chemical symbol or name followed by the mass number, because every neon is going to have 10 protons. So we really don't need to include it like we did in this previous notation. It's like, yeah, it's neon, it's 10 protons. So instead we can simplify this a little bit and write neon 20, neon 21, neon 22. And then if you want to figure out the number of neutrons, again, you just subtract the number of protons. And then we're also given on this little table the natural abundance. So percent of neon in a sample of neon, that would be 20, 21, or 22. You can see most of it's 90% of it would be neon 20, almost 10% is neon 22, and it's neon 21 that's actually the smallest abundance. And those are useful for calculating atomic mass. Dalton was a little bit off, stating that all atoms of a given element have the same mass. They have the same number of protons, but sometimes they have different numbers of neutrons. And of course, Dalton was working on a scale of grams, and he was working with sort of bulk samples, so they all would have had the same mass on average, because you would have these other isotopes mixed in. So we can calculate average mass, called the atomic mass, and that's that number we see on the periodic table. And that's why this is 35.45 and not exactly 35 or exactly 36 or exactly 37. Because it's a combination of abundance and the mass of those. A phone call. Okay, so we calculate this according to the natural abundance of each isotope using a weighted average. So naturally occurring chlorine is 75% chlorine 35 and 24% chlorine 37. And these are exact mass numbers. So to calculate the atomic mass, we're using what's called a weighted average, meaning I want the one that's more abundant to contribute to the average mass more, right? If we were to just do a true average, we'd add the two masses together, divide by 2, call it a day. But we've got another thing to factor in here, that whenever we go out and get any sample of chlorine, more of it's chlorine 35 than is chlorine 37. So when I calculate a weighted average, it should be closer to the isotope that's the higher abundance. So what that looks like mathematically is that we convert the percentage into a proportion. So you take the percent, divide by 100. So we get this decimal form. And so 75.75, and then we multiply that by the mass of that isotope. So this is not going to be exactly 35 even, because again, remember how they're like slightly, like a proton and a neutron aren't exactly 1 AMU. Add enough of them together, we get slightly different masses. So 0.7577 times 34.97 will give us 26.4968. And then we do the same thing, but now we use the decimal form of the percentage for chlorine 37 and its exact mass. And then we add those two together, right? Because to get all of it, this is like 75%. This is almost the rest, right? 25%-ish. So adding those two things together would give me 100%. So I take this one and I add it to this one, and we end up with 35.45. And that's closer to chlorine 35 than it is to chlorine 37. Right? So our natural abundance reflects in the atomic mass. Okay. So magnesium has 3 naturally occurring isotopes with masses of 23.99, 24.99, 25.98 AMU, in natural abundances, 78.99, 10%, 11.01. And this respectively just means that whatever order these masses in, they line up with these percentages. Let's slow down here. Excellent. Okay. So before actually we even calculate anything, you might have already calculated stuff, but is this mass going to be closer, is my atomic mass, so after I do all this math, is it going to be closer to 23.99, 24.99, or 25.98? 23.99, because this is 78.99% of it. So our number should be closer to that. And that's a good litmus test for your calculation, because a true average would be exactly in the middle of all three. Okay, so we can take each of these, and when we convert it to a proportion, divide by 100, you can rewrite them as 0.7899, 0.1000, and 0.1101. I like laying it out this way. And then I just multiply each of those proportions times the corresponding mass. So 23.99, 24.99, 25.98. This one's 18.94971. I think the other thing that's interesting when you actually do this math, and especially when you write it out this way, is you can look at the piece of that atomic mass that's being contributed by each of your isotopes. Right? So by far, 23.99 contributing to 18% or 18 of the total mass, whereas the other ones are like 2.5 to almost 3. And when we add all of those up together, get to 24.309099. How many sig figs? 4 sig figs. Because when we do these multiplications up here, that's the smallest number of sig figs, smallest number of sig figs, smallest number of sig figs. So this should be 4, 4, 4. And so it actually ends up being the decimal places in this first one that limit our sig figs at the end. So 24.31 AMU. The most common mistakes are forgetting where to add, forgetting where to multiply, and not converting percentages into a decimal form. And just remember this, like I said, litmus test of looking at your masses, looking at your percentages and saying, okay, whatever the highest percent is, my atomic mass should be closest to that AMU. So 24.31 is closer to, not by a whole lot because we've got this one also, but it's closest to 23.99. Shouldn't be exactly in the middle. So like here, just real quick, if I do the normal average instead of the weighted, assuming that I can type all the numbers incorrectly. So add them all up and divide by 3. That'd be 24.98. Really 24.99. So that's more directly in the middle of all of the values. Okay. That one should be review also. Okay, so what are the atomic number, mass number, and symbol for the carbon isotope with 7 neutrons? What would the atomic number be? 6. So atomic number would still be 6. Atomic number is Z. The mass number? 13. Because we've got 7 neutrons. So it'd be carbon 13. And then I guess the other way to write this out would be carbon 13 and 6. So how many protons are present in potassium 39? 19. Protons is always the easy one, 19. Or you can just look at the periodic table. Since the number of protons never changes, potassium's always going to have 19 protons. Now, how many neutrons? Yeah. So this one up here, that's the mass number. So mass number minus number of protons means there's 20 neutrons. Like almost done. It's just a periodic table showing you when each thing was discovered. There's a bunch of these. Like sometimes they got creative, like tantalum is named after like the Greek myth of Tantalus. Other ones though, not as clever. I think it's, scandium, yttrium. I think there was a couple others. Scandium and yttrium were discovered from the same chunk of metal that was mined out. Very similar chemical properties, so it took them a long time to sort them all out. Anybody guess why this is called scandium? Scandinavia. And then I think yttrium was either named after the city or like the county or something in Scandinavia that it came out of. And basically, there are like 4 different elements that all came out of the same rock. And every single time they discovered or were able to sort one out and identify it, they just named it after either the town or the city or the country or the region. Not very clever. Anyways, this is how they completed the periodic table. It's dumb, I know. Did you guys see that there's a kid that beat Tetris? You like play it all the way to the end and fill up the RAM until it actually crashes and dies. Kid was like 14 or something. Oh, you know what? I've got a great meme for this one too. It's not so bad in this class, although I might do this again. I want you guys to know the periodic table without having to like look at it, or at least have an idea of where things are. Can I not scroll down? No? Oh, here we go. It's too true. Anyways, yeah, Mendeleev's periodic table has less on it. And there's a lot of actually, you can look up alternative periodic tables. Everybody tries to invent their own version of it. The modern one works well enough, and it's more ubiquitous, more people use it. Just the end of this chapter is these broad classifications. So we break the periodic table up really into metals, which is most of it, metalloids, which are somewhere in between, and then nonmetals. So metals all have pretty similar properties. Good conductors, malleable, ductile, meaning you can stretch them into wires. Non-metals tend to be poor conductors. They tend to be non-ductile, non-malleable, meaning that when you try to smush them or crush them, they just crumble instead of deforming. Metalloids have a lot of properties in between. Semiconductors is what makes, they have intermediate electrical conductivity, and in the correct configurations, they have easily modifiable conductivity. So this is how like silicon transistors work. Is by passing a current across it one way, it causes it to be conductive another way. So you can turn switches on and off really fast. Another way to think of these is in terms of main group elements and transition elements. We'll talk some about transition elements, but most of our time is spent with main group elements. The main groups are called main groups because they have pretty consistent properties down a period. There's some consistencies among transition elements, but it's less consistent. Some named groups that you need to know. Noble gases are 8A. So far right column. Unreactive. The alkali metals are all reactive metals. The alkali earth metals are less reactive. And then the halogens, group 7A, are the very reactive nonmetals. And those are basically the far ends of the periodic table. So these are really reactive. These are really reactive. These are not very reactive. There's a really good reason for that. We also don't have chalcogens. I guess we can like just cap off ions on Wednesday, because it is 6:20. Okay, so I got to finish ions here, which really not a very difficult concept because we're just counting the charges. Just counting the charges between protons of the atom and the number of electrons. And anything that's neutral, oh yeah, we don't have a periodic table in here. Fluorine has 9 protons. I'll write it like this. Or I should say fluorine has 9 protons. How many electrons does fluorine have if it doesn't have a charge? 9 electrons. So if I have 9 protons, that's a plus 9 charge. If I have 9 electrons, that's a minus 9 charge. Plus 9, plus negative 9, 0. So fluorine with no charge is 9 protons, 9 electrons. So what this slide's saying here is, if we take anything that's neutral, so if there's no charge written in, then that's the neutral form. It has a charge of 0. A lot of times in chemistry, if it's 0, we leave it off because it's 0. Why do we care? Don't need to write it in. When we lose an electron or gain an electron, we're changing from either the neutral form, actually in both of these cases, the neutral form, and we're either removing an electron from that, in this case sodium, and creating an ion within a plus charge, right? Because sodium, in its neutral form, has the same number of protons and electrons. So if I take 1 electron away, that means that my sodium now has 1 less electron, and so there's going to be more positive charges than there are negative charges, and there's going to be 1 more. And then for fluorine, we're doing the opposite. We're taking neutral fluorine, we're giving it an electron, and that makes it the F minus. Because now we've given it 1 more electron, so we go from 10 electrons. This would be fluorine with still 9 protons, because that doesn't change, and then, not 9, 10 electrons. So we call positively charged ions cations. Call negatively charged ions anions. So our ion charges are always written as superscript, and this is something to watch out for. You always write it with the magnitude first. Magnitude first. followed by the sign. So if we had more than one, right here I just wrote them with, it's written with a plus or a minus. So if it's 1, you just leave the magnitude off. If it's more, so it's like calcium, and calcium forms a 2 plus charge, you put the 2 first and then the plus second. Same with the minus charge, so oxygen would be a 2 minus. Okay. On the periodic table, I don't know if I have a way that I can actually do this. On the periodic table, you're going to have, you got metals, non-metals, and metals almost always, probably for the purposes of this class, always form positive charges. Non-metals always form negative charges. So I think if I do, this won't show up in the video, but I should be able to switch between these. So we've got all of our non-metals over here. These guys form negative charges. Everything else will form a positive charge. So really most things form positive charges. Yeah, especially for the main groups. Does anybody remember which of these groups are the main groups? Groups meaning the column number. Huh? The noble gases is part of the main group. But it goes 18 down to what? 13. And then 2 and 1. Those are the main group elements. Everything else is transition metal. But even those, they're metals. They form positive charges for the most part. For these main group elements, we have a bunch that form cations that form predictable charge. The charge is equal to the group number. So that's going to be group 1 and 2. So what charge will group 1 form? 1 plus. Magnitude first. And group 2? 2 plus. So group 1 will form 1 plus, group 2 forms 2 plus. Again, oh, that's the wrong one. This one. On the periodic table, that's the alkali metals and the alkali earth metals. 1 plus, 2 plus. And then for the main group non-metals, and we'll talk more about why they want, actually, if you've taken Chem 20, you've talked about seeing why these form the charges that they do. It has to do with the numbers of electrons. Everything wants to be like the noble gases. What charges do the noble gases form? 0. They don't form charges. They're super stable. And that's because of the number of electrons that they have. So the fluorine, chlorine, bromine, iodine, they all want to be electrically, so in terms of the number of electrons, they want to be electrically like group 18 or the noble gases. So these guys all have 1 less electron than the nearest noble gas, so they want to gain 1 more electron. For these guys over here, they have more electrons than their nearest noble gas, and that's because, what's the nearest noble gas to sodium? Neon. Yeah, because argon's several electrons away, right? It's at the other end of the periodic table, but if I go from sodium, if I take away 1 electron, or if I go back 1 step on the periodic table, that's neon. So to be electrically like a noble gas, has the same number of electrons, sodium just has to lose 1 electron. So that's why it forms a 1 plus charge. Magnesium just has to lose 2. And it will be electrically the same as a noble gas. So that's why those form 1 plus 1 and 2 plus. So these guys will be 1 minus. What about group 16? 2 minus. Group 15? 3 minus. And then it gets a little bit weird because what's the closest noble gas for carbon? It's in the middle. So really when we're talking about forming consistent charges, we don't really talk about carbon or silicon or germanium. They're right in the middle and they could go either way. They end up, instead of really transferring electrons and forming true charges, They share electrons more than anything. And that's true the farther away you go from the noble gases. But for now, just remember 17 is, and the way that it's written on the slide is, it's the equal to the group number minus 8. Oh, this is talking about main group numbers. So these are the just like full periodic table group numbers. Actually, this works also. But if you subtract 10, then these become main group numbers. I think in the book, it'll be like 7a. But if you do 17 minus 18, that gives you -1. If you do 16 minus 18, that's -2, and so on. So those are charges. That's going to really be important when we start talking nomenclature, but not quite there yet. And then transition metals, transition elements, they form a lot of different types of ions. Their electron configurations are more complex. So what is stable is not always so consistent. And this is just reiterating that the 1A for group 1, group 2 are 1 plus and 2 plus. 7A is 1 minus and 6A is 2 minus. And here we go, you can see them on the periodic table. So we've just gone a little bit further. I don't know why they leave off beryllium. They do. Some other ones that form pretty consistent charges, ones that I teach in Chem 20 are scandium, which is 2 plus. And then aluminum is 3 plus, then gallium is a 3 plus, indium is usually a 3 plus, and then zinc, cadmium, and then silver is almost always a 1 plus. Those are all very consistent in terms of the charges that they form. No. So transition metals, like all of these in here, will form, for the most part, cations. And then like these ones that are being left out can form cations or anions, depending on if they're a transition metal or if they're a metal, non-metal, or metalloid. Yeah.
So why does hydrogen have 2 charges? Or like why is it shown twice?
It's a typo? Maybe? No. But helium's a noble gas. If you take organic chemistry, you'll talk about hydrogen with a negative charge. Because it can be, but I don't think we're ever going to deal with hydrogen as a negative charge. But if you think about it, like I said, if hydrogen wants to be like a noble gas, then gaining electrons would make it like helium. So gaining 1 extra electron would make it like helium. Most of the time, it loses its electron instead, and then it just has no electrons. So it's not untrue, but it is a little confusing. All right, so predict the charges of the monoatomic ions formed by these main group elements. So nitrogen. Is nitrogen going to be a, I know some of you know it, you're just not saying it. It's going to be positive or negative charge? Negative charge. How negative? 3 negative, 3 minus. Nope. And then rubidium. 1 plus. You write that as 1 plus or just plus. Okay. Any questions about charges? Yeah.
So you can write it just like if it's 1, you don't have to put the number.
Correct. You won't be wrong if you put the number, but you don't have to write the number.
I guess some people like it certain ways.
I'm not that picky. I will probably leave a note if you put the sign in front of the magnitude. So if it's -3, should be 3 minus. I don't think that's a deal breaker. I'd rather you just know the charge. That's what I care about more, but